We're in this apartment. I need some art on the walls or something. But these are like plaster walls? I don't know, stucco or something? It's not like I can drive a nail or anything into these walls. So I'd have to put up like a disc plate or something, you know? Something that has an adhesive and sticks to the wall or something. But I don't know. I don't know what I would put. It would be nice if I had some artwork or something like, um, but I'm not an artist and I don't really know any artists, so well, I guess technically, I guess doing like 3D graphics is kind of art, or it's very stylized at least. Um, you know, it's a piece of media, and that piece of media or something can have an artistic side. So, in that regard, I guess you're an artist. But speaking of artistry, today, to gain a little bit more experience with TSL, shading language, which is um, kind of like I don't know what you'd call it. It's not a real like language in the sense that it, was interpreted or compiled or something. But let's see what they call it. Yeah, it's a way to create shaders in three.js, and it's fairly new, but it is useful in that you can create your shader JavaScript side, kind of in the source code of your component. You don't have to get into GLSL or Wigzil or anything, and it will take your TSL code and convert it into something that can run on the GPU. So one of those shader languages. But last stream I felt like we were kind of fumbling on the TSL a little bit, and could use a little bit more practice in it. So that's the goal of today's stream. But the activity, I guess, that we're gonna do is we're gonna implement this kuwahara filter, which, let's pull up this and then let's make this bigger. So it's a tool for like denoising an image. Yeah, effectively reducing noise by blurring edges. So it's a convolution, I think that's what you call it. It's a filter over the image. So it's a post-processing effect which averages out pixels and tries to recover some, noises kind of blurred out because we're doing this convolution effect. And it was originally used, this is kind of interesting, it was originally used by this guy in Japan for medical imaging. And back then, they had really, compared to today, they didn't have really great hardware or software for, I guess, right here, dynamic heart muscle imaging. So the idea was that, like, well, we can probably get better imaging if we pass some filter over the original image. And I don't know if this worked or not. I don't know if that achieved his goal. I'm sure it did because it was probably published somewhere. But the mathematics behind it is that you create, for every pixel in the image, you want to put a box around that pixel. And then you're going to, this is kind of like the introductory kuwahara. Oh, you guys can't see this. I always do that, or you can't see what I'm looking at. Yeah, so to recap, it's a kuwahara filter post-processing effect, originally used in medical imaging back in the 70s and 80s. The math behind it is that you, for every pixel in the image, you want to put a box around it. So let's draw this out. Do I have it scaled at all already? Yeah. So here's a pixel. We're going to put a box around this pixel, and then we're going to look at 4 sectors. So this is, like I said, like kuwahara filter 101. Put a box around this, so we'll have 4 sectors. And then in these sectors, you can imagine are other pixels as well. So, you know, depending on how big this box is, we're gonna have pixels. Each of these littler boxes is a pixel. So let's just look at this first one here. You have pixels in this region here, and what you want to do is calculate an average color, and you want to calculate a standard deviation, and you do that for each of these sectors. And then at the end, you compare the sectors, the standard deviation, you take the minimum one, which means that it's not very, like its deviation isn't very high. So it doesn't have very high, you know, highs and lows and stuff. Well, it's pretty much kind of like, on average, it's about the same color. So you would use, you know, some kind of stats math and stuff to calculate that, whatever you do for calculating the standard deviation. So you loop over these pixels in this first region, calculate its average color. That's just, you know, adding up all the colors and dividing by however many pixels are in here. Same thing for number 2, you calculate average color, standard deviation. Take the minimum standard deviation out of all 4 sectors, and that is going to be the average. That's going to be the color that you set for this pixel here. So you do that for every pixel in the scene. And we're going to do that on every frame. So it's not a very efficient algorithm. And there's ways to improve it, and there's ways to get better imaging and stuff, or better results, but we'll take a look at that probably in parts like 2 and 3. So I'm going to do multiple streams on this topic. And luckily, there's been a lot of like work already done. So here's a article that we're going to kind of follow along with about the topic. And today I just want to implement this very first example down here. This code here is written in GLSL, but we're going to convert it to TSL. You can kind of see here's the effect. It looks like somebody did some like brushwork or something and drew this. And here's the original, so you can tell it's much sharper. The image has, you know, the edges you can definitely make out more so. You can control the kernel size, which in this case is the box size. So as you go up in box size, it gets a little bit more blurry. As you go down, you see more edges. The sharpness is kind of preserved. But you can kind of see it looks like it was kind of like painted with a paintbrush. And further down in the article, you get better results because, you know, a lot of people have worked on this filter, and a lot of people have improved it and made it more friendly for like shaders and edge detection, or like not losing the edges and stuff. So one of the downsides, which you can read about in the Wikipedia article, is the drawbacks and restrictions. You get things like this, or you get like artifacts and stuff. So there's a lot of like work that's been done to kind of reduce those drawbacks. And that's covered in the end of the article there, but we'll get there in subsequent streams. What else? So that's the main idea. The first thing to do, I think that is it. Let's see if there's anything to cover in the... This article has a lot of nice like interactive stuff. Like there was one where it showed the whole box. I'm gonna link another resource here, which is a video by Ace Rolla, which is a very popular like YouTuber that does stuff in the graphics, like not web graphics, but 3D graphics space. And he has a video on the kuwahara filter, and he kind of, goes over its history and the ideas behind it and how it operates and stuff. So check that out too. Goes into more detail than I will about how this is all calculated and stuff. Anyway, so let's create a scene that we can work with. Let's jump over to the code. And I've got this loaded up here. But I want to make a scene that will, for one, I want to have the like object in the scene rotating, because you'll be able to tell like by some of these drawbacks by this filter in the most basic like iteration of the kuwahara filter. You can definitely see some of its, like, you'll be able to actually see the drawbacks that it has. And one of those drawbacks is for moving images, where you're calculating the where you're doing the effect like every frame, you can kind of see the artifacting very well. And I also want an image that has, or like we're gonna pass in an image or a texture to this filter. So this is a post-processing effect, and I want an image that has, a lot of colors in it. So definitely going to use an environment map, and we'll probably use, well, I found a GLTF that we can use, so a model that we're going to load in, and it has iridescence and stuff, so it's definitely impacted by the environment map. So we'll do that here. Create two scripts. One for the module level, which is like module level stuff for this component, and then this script here is for like copies of this component. This is kind of like the instance, and then this is like static values or static methods on a class. This will only run once when the component is first used. But yeah, anyway, I don't try not to go into details, try to stay on topic here, but let's make a environment map loader. So this will be HDR loader. Well, let's do like this. Let's just get something to the screen first. I'm gonna give this, actually I'm gonna steal it. If you don't know where all this comes from, I have previous streams on these things, but we're just going to steal it from, probably this one's fine. And we'll clean it up and take out things that we don't need and modify it and stuff. So we don't have this, but we'll definitely need that, or we'll want that. Let's bring in our renderer. This is a helper function for setting the size and stuff based on the aspect ratio. We don't have an orbit yet, that's fine. Oh, that's good. So let's make a scene. Camera. Let's translate the camera back a little bit. Probably like, I think this model that we're gonna use, when I loaded it in, it was very small. So we can either scale up the model, or we can translate the camera very, like, it starts at the origin and so will the model. If we pull the camera all the way back here, the model's going to be very small, but if we only pull it back a very small amount, it should fill up the screen pretty good. So I'll just use one for now. That's why it's off the origin at least. And then we'll probably make this value smaller once we load it in. Let's make our controls, or our orbit controls. Pass it in the camera there. and then this is from a different file. We'll bring that in, and so is this function here. So everything's good. Now we need to put stuff in the scene. Let's actually put in the background and environment map. So we'll create an HDR loader. Here. And that URL, the HDR URL, that's going to be located at assets, HDRs, and then I'm going to use this suburban garden one because it's pretty bright. So there, and then down in the script down here, we need to load that. So we'll do HDR loader, load async, load it from that URL. This will return a promise, which will give us the HDR or the texture. Then we can set the scene background to that texture, and also its environment. But we need to set the mapping of this texture. So the HDR.mapping, that needs to be equal rectangular, I think it's reflection, it's one of these. I think it's reflection. Let me look at other files. Yeah, down here. You see that? Yeah. So we need to set this mapping, and then when this component is done, we'll just delete that, or we'll, dispose of it. So this is the HDR. Let's return HDR here, and then HDR.then. This might, well, so like if this were a library code, you would want to set the scene background back to what it previously was before you set it here. So you'd save that in a local variable, like, in a variable somewhere, and then maybe this scene is coming from, like props or something. Like this. And you modify the property of that scene here when this component initialized and all that. You want to, if you're going to destroy that component or take it out of the tree, then you'd want to set everything back to the way it was. I'm not going to worry about that now because this scene is created in this component and all this. But just be aware, like if, for example, like in Threat, that's what we have to do. If there is a component that like sets properties of some class somewhere, some instance, then when that component unmounts, you want to set everything back to how it was. Kind of restore what it was before. So HDR.then, we just needed to dispose of it. Here we'll get out the HDR, and we'll just dispose of it. This is a little helper function we can bring in, and close that, and there we go. Okay, we've got our HDR, now we need to put something in the scene. So let's bring in a DLTF loader. Let's see, that's a new, not import, well, we do need the URL, so let's do that. Assets, DLTF. This iridescent abalone, that's the one we're going to work with. Where's the music? Is it just really quiet? Oh yeah, I think it is. Okay. This is not that. This is GLTF loader. We got our loaders. Down here, let's load that GLTF model, GLTF loader, load async, GLTF URL. Again, this will return a promise. Scene.add gltf.scene. So that will put it in the scene. Make sure that's not too loud. That's good enough. I'll put it in the scene. I'm not doing anything with this. There it is. Pretty small. Let's put the camera a little bit closer. Maybe it's too close. Let's do like a quarter. Yeah, there we go. So this has pretty good coloring. It even has like holes in here, which that's where we're gonna tell like the limitations of the Kuwahara filter. We're gonna rotate this thing. And that's where our light source is, so most of the light is coming down onto it like this. But while it's rotating, we should see a lot of that like color, that like lighting and iridescence come through. So down here in the render loop, don't need to update that. We'll do this GLTF scene. Actually, we can either rotate the scene or we can rotate this object. Which means here we would need to like await it and get it out here, which we can do. Or we can wait for this. Because how would you do this? You would do, if you had to await it here, or you have to do a dot then here, you could like put it in some kind of variable. So here, you know, you just have some like GLTF thing here, and then when it loads, you set that equal to it like that. Or we can await it. Or if it's the only thing in a scene, we can just rotate the entire scene, because that's also an object 3D. So I'm going to do that instead. I'm going to rotate it along the x-axis, so, you know, in this axis here. And we'll just do, this takes in a angle in radians. So we'll do half an angle. So this will run every frame. Definitely want to slow this down. We can even put this in a variable. And we'll just multiply it. Well, this is like a factor, but let's do it like that, and then we'll do rotation speed. Now it's rotating. Let's rotate it in the other direction. Well, actually, let's move the camera off the axis. So this is kind of just along the z-axis. So we'll need an axis. Call that vector 2, or sorry, vector 3. And we'll normalize this axis for this vector. We'll pass this in here. We'll go off of it by 1. And we probably want to come a little closer, so let's do a quarter. And then maybe not so high in the Y. And then not so far in the X. Oops. Okay, I think that's good. Let me see when it comes back around. Yeah, you can see the light inside of the shell here when it like comes back around this corner here. Right there. Okay, that's good. So we got our scene set up. Now it's time to create the code. Or sorry, create the filter. So this is a post-processing effect. So this kind of takes the same shape from other things that we've done. Here. So there's a pass. What did we call it? We need a render pipeline. Yeah, here. So this code we're gonna need. Oh, I can get rid of that. We're gonna create it down here because this constructor here needs this renderer. Well, let's bring that in here. This is something from TSL. And then down here we need to make sure to dispose of that pipeline. That looks good. This texture thing, or this like first argument, this output, is going to come from the scene pass right here. So this is like when the scene is rendered, you get access to the texture. You know, it will put that into probably a render target, which you can use as input to other shaders. So that we'll do here. This, I want to move it up here where the HDR is at. I'm not going to worry about disposing of the GLTF, because in order to do that, you have to have, like, this has no shape. Because, you know, you don't know what you have loaded. You'd have to parse, or send this through, like, some kind of GLTF parser, and then kind of like what you do with schema validation libraries, like when you get form input from a client and you have to parse it on the server. It's the same idea. You have to send it through some kind of parser. Or you can kind of like go through the scene and you can traverse the scene and, you know, take a look at each child of, you know, objects in the scene and ask, are they meshes, are they textures, are they things I can dispose of, and so on. But I'm not going to worry about that on stream. But it is something that we should do eventually, and I have been thinking about that. To create like a function that's like dispose GLTF, or this would even be dispose like scene or something, and you pass it GLTF scene, and inside of the scene are like materials and geometries and stuff, and it would traverse that and dispose of things. You know, it would go down the scene graph and traverse it and dispose of things properly. But I think that's something I'll do off stream. Okay, so this pass, need to bring in from TSL. We have our output, and then we pass it into this texture thing. This UV, we're just gonna set to UV for now. So we should see the same result. And that's because what this texture does is it takes in, a texture, which is this output. And then this UV is just your standard UVs, you know, go from 0 to 1, and then 0 to 1 in the Y, and it just samples that texture. So here, if you want to do things with the texture, like, you can take this and do like 1 minus. Oh, I didn't expect that. I think you have to do 1 minus here. I don't know, somewhere like, so you can do a lot. You can modify these UVs. You can modify the color that you get out here, and so on. But here we're actually going to take this out and use it somewhere else, but I'm going to leave it there for now. Actually, what I'll do is this will be some function that we're going to call. Let's create that function here. So in order to do functions in TSL, you import this fn thingy. And this one's not going to take in any arguments, but it's going to return this. And same output. But here you can do something like return a vec4. Like if you wanted to output like a red color, for example. This won't look very good, but we gotta bring in vec4. Are we using it? Hold on. I'm forgetting to do something here. Oh, yeah. Down here, you need to call render pipeline dot render, or I think it's update. Oh, what is it? Render pipeline dot. I thought it was update. Oh, it's render. Okay, yeah, there we go. So, for example, take the texture of the output, pass in the UV, and we could do like 1 minus. I don't see anything. Okay, let's try that 1 minus here. Yeah, so that's just taking the, it's flipped along the X and flipped along the Y as well. But that's not what we want to do with with our output here. But we're gonna return a vec4 eventually. And I'm just gonna put in these as like placeholders. Okay, let's think about this. Let me go to the code that they've got. So they use like arrays and stuff, but you can actually do this without arrays. This get sector variance and average color function though, I think we're gonna copy that. So I kind of walk through this. So this is, taking some offset, taking some box size. That's the box size here. Where is it? Taking a box size, taking... Oh, is that a bug? Oh, no, it isn't. You see that? Yeah, that's good. This is outputting to average color and variance, so that way they can just write directly into that array. But here we're going to return, in our case, we're going to return a vec4 where the x, y, z of that vec4 are the color, and then the W component is the variance. So that's kind of the technique that's used. Let me see if I can find it. Yeah, this is the code from that Ace Rolla video. And then his sample quadrant is kind of the same idea, but they return in the RGB slot the color, and then the alpha or the W component is the standard deviation or the variance. I don't know if standard deviation and variance are the same thing. But if you imagine, like, if something doesn't have a whole lot of variance, that's probably going to be the color that you want to assign to that pixel. That means that overall in that region, there wasn't a whole lot of like variance. You know, everything was kind of about the same. If you had somewhere with a lot of variance, like really high highs and really low lows, you take the average of that, that's going to be blurring it pretty heavily. So you kind of want to minimize, you want to find the sector or the quadrant with the least amount of variance. I think that makes sense. But yeah, so in order to calculate the average, you need the sum, and in order to calculate the variance, you need the squared sum. So that's what they're doing in this loop here. They're getting all the averages and the variance and stuff. At the end here, they're calculating the variance as the dot product between that color and this luminance value. So we'll do that as well, but there's a luminance function from TSL that we can use. Once they get all those, it's been written into these arrays. Then they loop over the arrays and they find the minimum variance. You know, you're kind of doing the visitor pattern, I think it's called, but you visit every element in the array. You do a check if the minimum variance, like if that's less than the current minimum. If it is, then the final color you set to be the average color. You know, you got the index there, the I there, so it's just matching it up with the, you know, you index into the average colors array and set the final color to that. And then finally at the end, that's where you assign the pixel color or the output color, the fragment color to this. So this is just an alpha of 1, meaning total, like total opaqueness. There's no transparency or anything here. So it's pretty simple, but we're going to convert it into TSL. And I think step 1 is to create this function here. I'll put that off to the side. And then create that. It's kind of a long name, but I think it makes sense. Let's call it variance and average color. And that is a function. So this function is pretty weird. It has a bunch of signatures. If you take a look at function here, you've got 3 different signatures for it. So it's overloaded. And in the first case, well, the case that we're concerned with is this one here, where we've got arguments in the shape of an array. To kind of show you where that comes from, let's take a look at this document here. Function right here. So you can call this multiple different ways. You can pass in an array that destructures it on the fly. You can pass in an object. You know, here they pass in a timer, which defaults to the current time. Here you pass in RGB, which I'm assuming are numbers, but this is in TypeScript. Um, and you can also use it with this JS func. You got this node builder, so that will give you access to things about the material, I believe. Yeah. Parameters will always be the first, blah, 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 blah. You can find out details about the current construction process, so you can get information about the material, the geometry, and the object for this current like iteration or something. So this one's pretty neat, but I can't think of a way to use it currently. But uh, something to keep in mind is that you can get direct access to the material and geometry inside of this function. You know, if you were like changing the color node of something, or the like a lot of these materials in three.js on the web GPU side, they have nodes and stuff that you can replace. You know, with your own custom nodes and all that. But our case, we're going to use the array version. Let's go back here. This one is something we don't need. Okay, so that leaves it in the buffer. Okay, or the buffer list. Where is it? This is flat shading. We don't need that. So let's pull up that example there. So in their case, they're passing in an offset, box size, and then they're writing to these two like places in memory. In our case, we want to get the offset. We'll take in the same parameters, but we will actually return something from the function. So you type this like a normal JavaScript function. This will be actually a vector2. So the way that you denote that in TSL is like this. Give it like this node type, and it thinks it's coming from like the DOM. Like these are just like global types and stuff. You actually have to import it from TSL. Node. Is that right? Yeah, where's this coming from? Let me check my notes. I don't remember where to import this guy from. Oh, 3.webgpu. So if you take a look at this node, this thing is huge, but takes this t node type, and it's parameterized with that node type. This t node type is either a string or a null. I thought this is something we could tap into, but it is one of these types here. So you can tell it's just a union of strings. In our case, our argument is going to be of type vec2. That's this offset. So if I hover over this now, it thinks it's a node vec2, and that's what offset is over here. So going to this function here, we're gonna need color sum, which we'll set to 0 initially. Vec3 we'll bring in from here. And then a squared sum is kind of the same thing. Initialized at 0. The sample count is going to be constant. Here they're calculating it, but the sample count, you kind of know, because you know what the box size is, you're not modifying box size before this loop. if box size is 8, for example, you know that this is going to be ran 64 times. So your sample count here will get incremented 64 times. You don't have to do that in the loop though. You can just pass it in, or you can calculate it, or you can create a constant for it. Box size is 8. So they're using it as a uniform here, but I'm going to hard code it for now. And you can see here, the kernel size gets passed in, so this is the offset here. Kernel size of 8. We have the kernel size, and we need to multiply it by itself to know what the sample count is. I'm going to turn this into a float. And we'll pass in the box size here, and we'll do multiply with box size. Okay, so the way that you do loops is kind of interesting. Where's our document? Here? Oops. So loop, there's like the function, this thing is overloaded, so there's a couple of ways to do looping. And the most basic one is just you pass in a number here, you get out the index here, and then you can do things in the loop. Or you can pass in an object. And this would be like if you need to specify the type of the iteration variable. So I'm sure it probably defaults to uint here. Yeah, this is kind of like a while loop. So this is kind of like, what is it? Python's range function, I think. Like you can even go backwards if you're, don't let this message distract you. Continue with what you were doing. Then why'd you type it? But welcome to the chat. Yeah, so again, we're gonna use... Oh, okay. Well, how's it going? Oh, no, I did listen to you. I saw you. But sometimes, you see messages like that. What are you building? We're doing the kuwahara filter. You can type in today to see. But we're using three.js to do it, and we're trying to take this example. Yeah, this example and convert it to TSL. So this is written in GLSL code, and we're just kind of doing like a mapping of it to TSL. But it takes a model like this, and here's the original model with all its edges and stuff, and it kind of blurs it a little bit. But this is working towards a much more effective filter, which creates like this painterly effect. So you can see when the kernel size is low, which we kind of talked about in the beginning of the stream, you get the original look. But as you go up, you kind of blur it, but you get kind of this painter, like it almost looks like brush strokes. So it's a post-processing effect to give it like a stylized look. But right now we're converting this loop here into TSL. Over here in the source code. And the TSL document here kind of talks about how, you can use loop, but in our case, we just want to loop a certain amount of times, which is equal to the box size. And then here we get out something with an I. Let me bring this in. What am I missing? yeah, so this I should be, okay, it's an integer. That makes sense. And then back to the example here. So this offset, that's where we're going to index, or that's where we're going to sample from the texture. This texture comes from the, because it's a post-processing effect, this texture you get from the output node of your render pipeline. So let me show you that when I get this sample offset. That's going to be the offset.add. We'll make a vec2 out of the x and the y, but this is a double loop. So you get access to y and x. And then here, we'll rename this to y, this one to x. This will be y and x. And let's see. Need to bring in vec2. Let me format that. Okay, so we added to the offset. So down here, this kernel size, so they start is in the top left, so it's 4 sectors. So this is kind of like the initial offset, and then this loop here kind of goes through the pixels of that sector, and then you do it 4 times for each, or you do it 4 times, 1 for each sector. Where is it? So here's sector 1. You know, you offset over here to begin with, and then this loop is going through the pixels. And then same here, this offset over here, going through the pixels. And that's why they call it 4 times. So the initial offset needs to be done here. And you can see that it's a vec2 and they're passing it as the first argument. The kernel size, that's our box size. So this is an 8x8 sector. So that's where we get our offset here. And then they use it as a sample. This is like the index to sample into the texture. But you can't just use UVs for this. So to get the color out, we know that it's going to be texture. We know we're going to pass in the output. But what do we pass in here as the UV? Can't use UVs, like you can't take the UV and scale it up to the screen size. That's because the UV, like the actual coordinate, needs to be offset, not the UV. So you can get access to this screen coordinate from this helper function. What is it called? Screen coord, I think. Oh, screen, there it was. There, screen coordinate. We're gonna add, that's a vec2. We're gonna add to it that offset, or that sample offset. And maybe not sample offset, maybe we'll just call this, maybe we'll just inline it. Okay, like that. And then once we offset it, that's this part here. You need to divide out by the screen size. So we added it here. We need to divide. And this is also something you can bring in from TSL. So I think that's correct. That's going to be our color, which we take here. Now we're going to add it to the color sum. We need to use add assign here, because if we just do add here, it will return a new node or a new vec2, and then we just lose it, like we're not assigning it anywhere. But to do like plus equals in this case, use add assign. And then that's the color that we got. And then the squared sum, or squared color sum, add assign. color dot multiplied with itself. Oh, let's see. Oh, this is a vec3, that's correct. Oh, we need to get the RGB out here. So this here will return a vec4, but it needs to be RGB. What happened here? This needs to go down here. Like that. That's good. So, adding it to the color, adding it to the squared color, which we're going to use to calculate variance. We're not going to do this because this is something that we know ahead of time right here. At the end here, we're going to take the color sum. This is, you know, what you would do with averages. Remember that this is a vec3, but we can divide out component-wise the sample count. And then we can assign that to the color sum. That's our average color. Probably just do this. Now this variance result, I think that's what res stands for here. Let's just call it variance. We'll take the, this is just, you know, variance calculated from, I think it's variance. Yeah, I think it's this one. I don't know, it comes from statistics. I don't know if it's standard deviation or variance here, but that's what they're calling it here, is the variance, so let's call it variance. Take the squared, color sum, divide out the sample count, and then we're going to subtract the average color squared. Oh. That's the variance, and then here's where we're going to return the vec4. The RGB of this vec4 is the average color, and then this is variance. We're going to take the luminance of the variance, which is what they're doing here. So this is a constant value, which is perceived luminance, RGB. So you can see blues are supposed to be more luminescent, I guess, than the others. This is normalized. You can see that greens aren't very luminescent or something. This is, you know, I don't know. You can find this online. You could just search up like perceived luminescence and stuff, and these numbers come from somewhere, but we're just going to use them. We're not going to worry about where they came from. That's the variance. So if you take a look at this guy, it's now returning, I think this is the return type, or maybe this is, but it's returning a vec4. So if we call it here in the function, pass in the offset, this is the minus kernel size, minus kernel size. Let's just do 0, 0 for now. This is, in our case, box size. This, we'll call Q1 for quadrant 1. Yeah, it's returning join node anyway. This is a vec4. So you can call .rgb on it. That'll return a vec3. You can call .w. This should return a float. So this is effectively a vec4 for that first quadrant. Or actually, I think this is quadrant 4. Because 0, 0 is in the middle. Here. So we did an offset to begin with. So we should probably do these in order. This will be negative, like negative kernel size 0. Or maybe positive. Let's see how they do it. I think they do it in order. So we're just going to copy these. Box size. This one we'll keep. Okay, what do we have here? We've got 0. Box size, and then this one is box size 0. What's our third argument? Oh, this needs to be a vec2. Probably do this faster, but oh well. Okay, we've got our variance and average color for each sector. This is where I'm going to deviate a little bit and be more in line with this code here. So that's our Q's. We've got the same thing here, the Q's. We need to find the minimum standard deviation. So doing it this way will avoid that for loop and that if check here. It's the same idea, but I think it's a little bit more elegant in this case. So this minimum, we have that in TSL. We can say min variance. That's going to be the minimum of q1.w, q2.w, q3.w. Remember, this w holds the variance because this is a vector 4. In the first 3, the RGB or the XYZ is the color, and then in the W slot is the variance. So this is the minimum variance, but we don't know if that is Q1, is that Q2. We don't know which one. So here, I think this is particular to, like, this is done in Unity, I believe. You can actually, like, this .a is the same thing as .w, so in a color, like if you interpret it as color, it's the alpha value. If you interpret it as positional data, it's the amount that you divide. This is kind of off topic, but it's what you divide to get, like, perspective correction and stuff. So, you know, if I call this .a or .w, it's the same thing. But you can, this is interesting. What they're doing here is, this is like a Boolean here. So it takes each of these, compares it to the minimum standard. If it's equal, it'll set it to 1. If it's not, it'll set it to 0. So I couldn't find in TSL a way to do this, but we can do it. It's just a little bit more long-winded. So you would create, you know, your Q. This would be some vec4, but we'll take q1.rgb. Or no, we'll take the W. We'll say, is that equal to the min variance? Now, if you take a look at this, this returns a Boolean. This equal thing returns a Boolean. So we can put it into bvec4. Probably wants these other ones to be filled out. Oops. How do I do this? It's B. I have a key map to get this. I don't remember what it is though. Is it A? Okay. I just want this part of it. Let's do this. These are all going to be the same, but they're going to be Q2, 3, and 4. Okay. This is a, vector 4 of booleans. So this is asking, was Q1 equal, was its W, which is its variant? Is that the one we're looking at? Is Q2 the one we're looking at? This will be, maybe it's true, false, 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 or maybe this one was true, or whatever. But we're going to use this Q here as math right here. So we probably don't want it to be a Boolean, we want it to be a float value. So you can say 2 vec4. And this could probably even be u vec4, but I'm gonna leave it as 2 vec4 for now. That gets us back to a vec4. And now we can return vec4. We're going to take the Q1, and because these are booleans, or these are zeros and ones, you multiply, well, let's get the RGB. If you multiply by 0, this will go out. This will drop out. This is going to be, here it's 0 plus something. Maybe it was this one, that was 1. No, one of these is going to remain. Everything else is going to drop out. So, still playing music? Did we lose it? Oh yeah, we did. Okay, there we go. Yeah, so we'll multiply it by Q1, or actually we'll multiply it Q dot X. So if it was 1, this will remain. This is the same thing, Q2.RGB.mul Q2.X. No, wait. Yeah, this is X, this is Y. Yeah. So, because we have 4, we can fit it into a vec4. The X component here corresponds to Q1, Y corresponds to Q2, and so on. And then this is adding it. I wonder if there's a faster way to do this. Because this is almost like the dot product, right? I'd have to look at it, in depth. Q1.RGB, multiply that, .add. So it would be nice if we could use operator overloading, but we're in TypeScript, so we can't. Eventually I want to take a look at type GPU, and this actually has this has a way to do type overloading in TypeScript for I don't know how to show it very quickly, but you take my word for it. It's got a way to do type overloading, but it uses a thing called TS over. Yeah, right here. Which is a plugin, I think, that allows you to do operator overloading. So that might be, I kind of want to look into that eventually, because I have a feeling that this type GPU thing, because it has a TSL, yeah, right here, this 3, you can write stuff in TSL. Yeah, 2 TSL right here. So you would write your normal like TSL or type GPU code, and it would output, you know, TSL that you could use. This is cool that we hover over it. Gives you documentation. That's nice. So here's like a really basic example of writing type GPU code, but assigning it to a color node in three.js. But we're not there yet. So for now, we have to do it with these, you know, chaining methods. But this is going to be q3.rgb.mul q.z. And I don't know if this formatted it properly. Okay, that's correct. Alright, let's see, what did I mess up here? Is that it? Was I happy with that? Oh, okay. So I wish it would put this on one line. But I guess that's fine. Let's see if that is working or not. Here. Yeah. I think it is. It's hard to tell. It's always hard to tell. But let's make this bigger. I believe it's working. We can see there's artifacts happening. If we pause this, I don't know, there's definitely some funny business going on with these holes. You can kind of see where, wait for it to roll back around. Maybe I'll make it a little bit slower. There's our speed. Let's bump this up to like 300. Like if you look at the holes and you get the right angle or whatever, as it's rotating, you can kind of see it's not so great on moving pictures. Or like rotating objects or anything with movement and stuff. This filter currently doesn't do a good job. I mean, we can fix that, and that'll be a topic for next stream. But it even applies it, so it applies it to the whole image. It even applies it to the background here. And if we want to turn this into like something that you can enable or disable, so here where we're taking, well, we can either like check for that boolean here, and then just early return. That way we don't do all this math. That's probably the best way to do it. Because, or what you could do, and I don't know if like shaders are this smart, but you can imagine that if you had two colors, let's say, and you wanted all of the first color to come through, but none of the second color, you could create this here where you'd had like color 1 multiply 1 plus color 2 times 0. So this would mean that this term drops out entirely, and all you're left with is this one here. Or you could do it like this. And because that Boolean, 0 is false, true is 1, you could pass in the Boolean here. You could do like 1 minus whatever that Boolean was. Here it would just be Boolean. But I don't know, if you do this, let's say this is some really expensive calculation, I don't know if it's smart enough to look ahead, or even to do this, and say, well, anything multiplied with 0, this is just going to drop out. And then skip all, like if this was some really expensive computation to get this color, we're not going to use it anyway. If this Boolean is 0, we're going to drop this whole term out. I don't know if like web graphics is, not web graphics, but I don't know if these languages are smart enough to do things like that. Or you can just be done with it, and you can just say like, if, see if I can bring this in. Boolean node, can we just pass in true here? No. Texture, output, UV. Is that what you want? Maybe it needs to be Boolean, I guess. Yeah, I think TSL you can do ternaries as well. So that might be a way you could get around that expensive computation. And I think ternaries are supported, but only like really basic ones. Oh yeah, okay, yeah, it has a select thing. This is interesting. Because here, if this was like true or whatever, we take the first one, we skip over that calculation. If this was an expensive calculation. If it's 0, then we have to do it. I don't know if this select come from... Okay, yeah, we can import it. Let's bring this down here. Let's return select texture. Oh wait, this is going to be the Boolean, so what do we call this? Enabled. This will be a uniform that we pass in. So I'll make one in a moment. Enabled, if it's true, we want to do this. And if it's not true, we're going to take the texture, and this is just the normal output. So where does that enabled come from? Okay, let's see if that works. uniform you have to bring in. Okay, so that's enabled. That's disabled, or that's not enabled. So now what we can do is make controls for this. Oops. Let's put this in a div. That is relative. Pane container. Yep. Bring that in. This will make absolute. Put it at the top. We'll move it over to the right. Here we'll add the attachment. What is coming out here? Okay. This is the configuration for that pane. The title, we'll say this is roles for now. So we should see it. And then the second argument to this thing is the initialization function. So we get the created pane. Let's add a binding. This object, I think we can just pass in uniform here. Or let's pass in enabled value. Oh, we need to give it a name. What's the name? Oh, I think label. Label is enabled. And then probably just call this uniforms. Okay, so if this is working, then when I turn this off, yeah, we go back to no effect. That's pretty neat. Then I want to give controls to the rotation. So this will be kind of the same thing. If this is true, then we'll rotate. If it's 0, then this drops out and we didn't rotate by anything. So this doesn't need to be... So you might ask like why I'm not using state here. And the reason is that providing state, like you kind of have to wrap the state in an object or a class or something to use this way of doing like bindings and stuff with tweak pane. So this comes from this tweak pane library. It's kind of a wrapper around this thing here. And I thought, you know, maybe we could use like getters and setters here. But in practice, it didn't work out. Like it looked like it would work, but it would cause these... this runs inside of an effect, and you're not supposed to set state in an effect. So setting the state here, I think it would trigger, like you would have to untrack it and stuff, if you're familiar with Svelte and all this. Reading from that state or modifying that state would cause this to rerun. and it would recreate that pane and stuff. So, but in a callback, you don't, like, you can read and write to state inside of a callback, that's fine. But this doesn't need to be state because we're just picking up the current value that it is inside this render loop. There's nothing that needs to react to that state. There's nothing in the DOM or whatever that needs to be updated. Because this render loop or whatever just runs in a request animation frame. So we can get away with just saying, we'll say that that's set to true by default. And so down here, we can just convert that to a number. So that unary plus operator just converts its argument to a number. In the case of false, it'll go to 0, and true will go to 1. And I think anything that's not 0 or not false or something will get converted to 1. Or yeah, it will get converted to 1. So if you do like this, oh, I don't know then. Let's see, well, this. So there's something that happens when it does that conversion, I guess. Yeah, it's some weird JavaScript thing. But if you're interested in all that, because I don't like to use the number constructor, you could also just do this. But I think that's this number constructor thingy. The plus does more of what we want it to do. Unary plus, I guess. So this thing is built for this. So that's what I'm going to use. But yeah, it does number coercion. This is kind of off topic, but yeah, you can read more about it in the MDN docs. So if rotation is enabled, let's say probably want to put this inside of a folder. Folder equals pane dot add folder, isn't it? Add folder. What is it? I think it's add folder. Where's my? Oh. Yeah. We'll take that uniforms folder and we'll put this inside of it. This one we'll just call, I don't know. I don't know what to call this one, because it is kind of just like the controls. So maybe I'll just add it to the main like folder, I guess. Here, this will be... We can actually make this a little simpler. We'll do it like this, because this expects an object. Rotation enabled, value. Label. Rotate. That's a Boolean, that should be fine. But down here, we need to read from value now. So I don't know if I need to wrap this or not, but we'll do it just in case. So if we don't rotate it, yeah, it stops. We're still rotating it here, but this term inside of the parentheses turns into 0 when it's false. I wonder if you can, what would be pretty neat, but again, off topic, because I kind of did what I wanted to do this stream anyway. Now it's just making this demo a little bit nicer. Is to specify the axis of rotation. And I don't know if TweakPane has a way to do that, but it has these plugins, and one of the plugins I think is a point. But no, you can just, not a plugin, you can just use it. But I don't know if they've got a 3D point. Okay, here we go. 3D. This is really nice though, where you can just kind of like set the axis, but I don't think you've got it in 3D. If it's a 3D point, it goes to this like range selector. And because that axis is in 3D, like let's like what axis do you want to rotate around? Right now we're just rotating around the x-axis. That's this rotation here. Rotate around the x-axis. But then again, like, do they really need to set, you know, what axis they can rotate around? You would probably want to do that if you were demonstrating like rotating objects or whatever. This example's not about rotating objects. But if you want to stop the rotation and look at it in more detail, there you go. So I'm kind of curious what happens if we scale this mesh. If we take this scene, let's take this GLTF scene. Now we'll take the camera back a little bit more. But yeah, it's like, I'd like to look inside of it without it getting clipped. Like that. But I don't know if like scaling it, I mean you have to do some kind of, whenever you downscale or upscale or something, right? You have to say, what do I do with those extra pixels or those extra, you know, extra pixels or loss of pixels? Because this guy or whatever is probably reading from a texture to get its normals and its displacement and all this. That works fine if I display it at its original like intended size, but what happens if I scale it up? Now I have more pixels to work with. Now I have a bigger like surface and all this. So in that case, that's where like your MIP maps and stuff come in. So whenever I'm like scaling stuff like this, I'm kind of always like, should I really be scaling it, or should I just move the camera closer to the object? You know, if this is the only thing in the scene, I can return the scene from this. But how do I apply the environment in the background here? So I could load these in parallel. You know, doing something like promise.all. So let's do that for a moment. So yeah, what this will do, if we do it this way, We wait for both of these to finish. We'll do everything in the dot then. This will become just one big dot then. We'll return the scene from that. But then I won't have the scene available when I go to render. So maybe it's best to leave it like this. That way down here when we render, we always have the scene ready to go because it's been instantiated already. Otherwise we'd have to wait for this thing. I don't want to wait for it because I can, like, while that's happening or whatever, this will happen in a callback. You know, I could set up all this stuff here. I can set up the renderer. I could set up its animation loop and all this. If I were to await it, you know, down here like this, for example, a promise, then, you know, it would wait for those promises to resolve before it could do any of this stuff in the attachment. Oh, let me put the camera closer again. Now, if you're using, you know, you can write your shaders like this by hand. It's good practice, I think, to kind of learn it. But if you're just using it for an application and you just want this effect, this is already implemented in these libraries. Like three.js already has a kuwahara filter for you to use. And so does post-processing. They've already got one as well. I don't think there's a demo page for it, but let me see if I can find it. Yeah, wait, that's a blur effect. I'm pretty sure it's in here somewhere. But I don't want to look for it. But that's where this trace.js one is getting it. And I think this has like first class support for React 3 Fiber as well. But all these kind of things are out there in the wild already. We don't have it in Svelte, but you can use the post-processing library to achieve the effect in Svelte. I think we've got an example here. This isn't the kuwahara filter, but it brings in stuff from post-processing right here. So you can import that effect. You can create your effect composer here, and you can use that effect. Yeah. So I can't think of anything else I want to get accomplished that would be pretty quick. I guess we'll kind of recap how this effect works and what's next. So going through this article, we've done this first one here. Oh, I guess I could change the kernel size. Maybe I could apply that. That would just be another uniform. Let's do that real quick. That'll be easy. So this box size is hard-coded here, but we can create a uniform out of it. We'll default to 8. And then everywhere where we pass in the box size, now we need to do mul -1. So let's call this or maybe just box size negated. I don't know what to call this, but I'll call it box size negated. That's box size.mul -1, so we don't do this. We pass in now everywhere that has a box size. Actually, we can grab a hold of minus box size and replace it with, we'll do that for the whole line, I think. How do you do that again? Oh, what is the... G, that's it, for global. And now this thing, it, you know, it's expecting a number here, but box size is now a node. And because we have box size, we probably don't even need to pass this thing in. The offset is what changes. The box size is constant. So we'll just do that. Now we don't need to pass this in. If these functions were pure, which is maybe a topic we can tap into, or you know, if you wanted to move this into its own file, then you would have to take everything, just like JavaScript, you'd have to take in all the arguments. Can I do .value? Yeah. Ah. So let's make sure this still works. But now we can do the same thing here where this box size is something that we can control. So enter uniforms. Let's see, let's create a uniforms. No, let's not do that. Let's do that. We'll do uniforms. Folder.add binding. Box size value. Kernel size, the min I'm going to say is 1. The max, we'll do like, I don't know, what's a good number? Let's do 16. Step of 1. So if I bring this all the way down, the luminance takes it takes a lot of illuminance. So I'm losing a lot of the brightness. Is that what happens here? No. I'm surprised you can't just pass in box size here. That might be the what reason. Oh, look how slow it is at large kernel sizes. Ooh, it's so slow. See, theirs doesn't have that problem. I'm not sure what's happening here. It might be this loop. Um, no, it's still slow. That's strange, isn't it? Okay, well, in that case, that's something to explore. Let's go back. Well, it's slow because of the rotation is slower, but it's not choppy. Yeah, this was 2.25. Okay, I think we'll summarize and then we'll call it here. The way that this kuwahara filter works currently, and we'll improve it as we do more streams, and that's later on in the article down here. But it creates a box. So for every pixel, we create a box around that pixel. Well, we create sectors around that pixel. Let's draw it. So we got 4 sectors. And what we're going to do is calculate the average color of each sector and the variance of that color, of the colors in that sector. So you would, to get here, you do minus kernel size, and I guess minus kernel size on the Y. So this is 0, 0, let's say, or this is some, location in the texture, whatever. To get here, we go back and up. This is laid out where Y is positive, Y is down. So to get here, that's where we do minus box size, and we're gonna loop over that box. That's what we do here. So for every X and Y, we get the color of that pixel. We can do that by sampling the texture, which is what we have in this output. But we need to calculate that offset, so that's where we calculate the offset here. And then this is in the range 0 to 1, so we take, the offset. We know that this will be within that range. And then we scale it, so that's 0 to 1. We take the color out of the texture there. Get the sum of all the colors. Get the sum of all the squares of the colors, because we're going to use it when calculating the variance. Once we do that for every sector down here, we find the minimum variance. So these Qs, Q1 through 4 here, are vec4s, where the RGB is the color, and then the .w or .alpha is the variance. So we find the minimum of all the variances, and then we don't know what variance it was, we just know it. We don't know what, color, we don't know which Q here. This doesn't return the Q, this returns the actual value. There's no, min by or something like that, which would be cool to have, but we don't have that. So we have to find out which one it was, and we do that by asking if any of these were equal to the minimum variance. This will give us kind of almost like a bit mask or something, where it's a value of 1 if that is the minimum, and then everybody else is 0. We take that and we pass it in here, where we multiply the color value by that 1 or that 0, and then we sum them up. There should only be one non-zero in this sum, because all these others will drop out if they're minimum variance if their like thingy here is equal to 0. And then we set that to be the color. This variance here is using the luminance of the variance, which they do here, but I don't know if that's actually correct. If you take a look at the Ace roller code here, they calculate the luminance on every pixel. We look at sample quadrant. Yeah, every sample that they take the luminance of that sample, and then they use that in the color sum. So I might play around with that and see if we get better results. If you take the luminance of an average, is that the same thing as taking the average of all the luminances? I don't think so. They also do like saturation and stuff here. So more saturated colors, you know, brighter colors and deeper colors and that sort of thing. Yep, that's it. So next stream, we will take a look at the part 2. I think this might be a 3 or a 4-part series. But in the next segment in this article, they do this technique where rather than taking the like box thing, which we talked about here, they do this circular like sampling, a circular kernel. And the math behind this is a little bit more complicated, but because we already have this sample or this calculate, like this already broken out into a function, we can just replace like what we loop over here and how we get the averages and stuff. We can kind of replace these loops with what they talk about here using a circular kernel. And we'll talk about like how, like what this does, and if you've already watched the Ace Roller video, it tells you about all that. So we'll implement that, and probably we'll implement this Gaussian weight distribution, or this because right now everybody is weighted the same, but you would want pixels that are closer to the pixel that you're working with to be higher weight rated. But this Gaussian is a pretty expensive function to calculate. You can approximate it with a polynomial, which is, you know, much simpler, faster, at the cost of being like less accurate. And then the last, like maybe the last stream, is how do you do this anisotropic kernel. That one is a little bit more complicated. You have to do like Sobel, you have to use a Sobel filter to get edge detection and stuff. So that'll be probably parts like 3 and 4. Yeah, I think that makes sense. So I'm gonna call it here. Next stream will be Saturday, I think. Depends on if I can prepare all this by Saturday. So tomorrow's Friday, and then Saturday stream. So I think Saturday is okay. If you're still here, thanks for watching. Hope everybody has a good weekend. I gotta give my mom a call because I told her I'd call her on Thursday for Mother's Day, and she said, okay, sounds good. So that's what I'll be doing when I get off stream. Everybody take care. I'll see you Saturday.